Hello everyone. Today we're going to introduce you the hydraulic chamber and orifice components in hydraulic system modeling. In this lesson, our learning objectives are to understand the calculations associated to hydraulic chamber and get familiar with equations of pressure and flow rate calculation in an orifice. Let's start with a typical hydraulic system where a pump acts on a hydraulic jack through a directional valve. This system regroups classical components found in hydraulic systems: pumps, lines, orifices, chambers, valves, and hydraulic jacks. Hydraulic chambers are capacitive elements. They can be found in classical chambers, but also in accumulators or lines. The hydraulic chamber can have constant volume as well as variable volume. The inputs of chamber are flow rates entering inside the volume, and the output is the pressure inside the volume. The general equation behind a hydraulic chamber with fixed volume is shown below. So B is the bulk modulus, which represents hydraulic stiffness. For variable volume chamber, you can check the help document for equations. There are two kinds of losses exist in hydraulic components. One is singular losses, or local losses, which happens at restrictions, orifices, expansion, or contraction due to disturbances. The other one is regular losses due to viscosity effect, and regular losses occur in pipes. Now we'll introduce how the equations of orifice are derived. From Bernoulli's equation, under the assumption that there is no energy loss when fluid passes the orifices at the restriction in the middle, as shown in the figure, the total pressure will recover if the flow areas, heights, and static pressures are same at both upstream and downstream positions. But there will be always energy loss, and what man can observe is P3 is less than P1, because when fluid passes through the orifice, local disturbances happen, and it causes energy losses in this region. So the Bernoulli's equation will need to add a pressure loss term on the right-hand side. As introduced from previous slides, there are two types of pressure losses. For the regular losses in hydraulic network, the pressure losses are expressed as function of the fluid velocity u, density, and the friction factor epsilon, as shown in the equation 3. This equation is mainly used in components from HR library. In flow control components, another equation, shown at bottom, containing a flow coefficient CQ, and is the most frequently used equation in both hydraulic library and hydraulic component and design library. AR is the cross-sectional area of the orifice, ρ is density, and P up minus P down is delta P across the orifice. We're familiar with these terms, but what is CQ? There are two types of flow regimes defined in fluid mechanics, depending on whether inertia or viscous effects dominate. It's a laminar flow when the flow pattern is smooth. In this situation, the viscous force inside fluid is strong enough to limit the fluid particles flowing only along one direction. When the fluid is turbulent, it means the fluid motion is random and has turbulences. Due to strong inertia force, the fluid cannot be constrained in one flowing direction anymore. The two flow conditions are related to Reynolds number, Re, is dependent on flow mean velocity u, hydraulic diameter of orifice, and viscosity, and the transition between these two regimes is done through the expression of flow coefficient Cq. The flow coefficient Cq is obtained by experimental tests or CFD calculation. As shown in the figure below, there is a critical Reynolds number. When Cq is lower than this critical value, the shape of Cq is almost linear and the flow regime is laminar. When Cq is higher than the critical value, Cq is at its maximum constant value and the flow regime is turbulent. Now, as a summary of flow rate calculation in orifice, we have the following equations. These are the most important equations for orifice, especially the last one. Please do memorize these equations. They will be helpful when you are going to tune your own hydraulic system model. Please also notice, except for conventional use of CQ for pressure drop and flow rate calculation, there are also 4 other options in orifice component. For more detailed description of these methods, please refer to help document. In this lesson, you have learned the calculations behind a hydraulic chamber and an orifice. Moreover, you must know the meaning of flow coefficient CQ, which can determine the flow regime, and the flow rate calculation in an orifice for different regimes. That's all for this short lesson, hydraulic chamber and orifice. Thanks.